In this video, we will talk about the various jet streams around the globe. We'll also talk about ocean currents that mainly affect the North American continent. And we'll also talk about teleconnections, things like El Nino and La Nina that we use for outlooks when trying to put together a winter outlook. Okay, but first up, we'll talk about the jet streams. They are located in the upper part of the troposphere. They do go around the whole globe, therefore they're thousands of kilometers long. They can be hundreds of kilometers wide, but only a few kilometers thick. Now the speeds, most often they are greater than 100 knots. Sometimes they'll be greater than 200 knots. The wind speeds typically will be greater during the winter season in the northern hemisphere when we have a larger contrast between the cold temperatures up in the polar regions to the warmer temperatures in the tropical regions. So the jet stream will form in this area between the cold air north and the warmer air south. And if you note the configurations of the blue versus the yellow, the cold air aloft associated with the troughs, the warm air is in the ridge, and here we have another trough over here. So these jet streams form due to the interactions of the imbalance of the cold air north, warm air south, the earth rotating, and the differential heating between continents and the open waters. So we have two main upper level jet streams that's presented in the book. The polar jet stream, we did talk a little bit about that earlier in this chapter. It is aligned with the polar front on the surface, which was located around 60 degrees north. And then we have the subtropical jet stream a little bit further south, and this can be more aligned with the subtropical high region around 30 degrees south latitude. There is a third one that does show up during the winter season on occasion, and that is called the Arctic jet, but your book did not talk about that particular jet stream. Now, what are the importance of these jet streams? Well, they will separate different types of air masses. To the north, up in this region, you'll have pretty cold air. We will talk about air masses in our chapter number 11, but the air mass up here could be Arctic air masses or polar air masses. Then in the middle, it's a little bit warmer. Subtropical type air could be located in that region. And then to the south of the subtropical jet stream, that's where you'd have your tropical air masses. So these jet streams will show us the separation between these various air masses. And I'll give you some examples of that in a bit. Take a look at a cross-section all the way from the equator here, working our way towards the North Pole way up here. The Hadley cell was turning between the equator and 30 degrees north. And then we had the Faro cell between 30 and 60, and the polar cell between 60 and 90. Now note the purple area here. This is the tropopause level, and the tropopause decreases in height as we work from the very warm air at the equator to the colder air at the polar regions. So the depth of the atmosphere does shrink as we work from the equator towards the poles. Now stuck in between these various cells, or what I call leaves, that's where we'll find the location of the jet streams. So the subtropical jet stream, if we draw a line over, it's roughly around 40,000 feet, and that's going to be associated with the weather map at 200 millibars. The polar jet stream is a little bit lower, so it's a little bit closer to the surface of the Earth than if we draw a line straight across. That one's going to be more aligned with 30,000 feet, and that would correlate to the 300 millibar map when we were looking at the upper level charts. Uh, okay, so let's continue on and take a look at a cross-section of the polar jet stream. It's going to lie in that region where we have a fairly good slope between the 500 millibar level. So here's the warm air going on the other side to the colder air. And so the jet stream is situated where we have a good temperature gradient from south to north or north to south. And with that temperature gradient, you'll also set up a pressure gradient. And these high altitude winds like to be up just tucked underneath the tropopause, because that's where the frictional factors would be the less. Remember, friction was the greatest at the surface and decreased with height. Now what we can do with the axis of these particular jet streams, if you come straight down to the surface, notice that if the jet stream was straight above you, the jet axis, you would be in the colder air on the surface. The warmer air is over here. So I'll point this out with some current weather maps here in Grand Forks. So this particular one that's out of your book, it shows the jet stream, and this would be the polar jet stream. So on this side would be the warmer air, on this side would be the colder air. This jet stream is a subtropical, so it's going to be a bit warmer here, and maybe even on the hot side over in this area. So from this, if I was just going to give a general temperature forecast, I would say that eastern North Dakota and Minnesota area would be on the colder side or below normal temperatures, and most of the peninsula of Florida would be above normal temperatures, since the subtropical jet stream is actually a little bit to the north of the peninsula. So here's a weather map for, let's see, 00 on the 4th. Local time, that would be 7 p.m. on the 3rd. So this would be Friday at 7 p.m. Grand Forks located here. And this is the polar jet stream. And this one is the subtropical jet stream. So under these situations, there's a ridge here and a significant trough in here. By the way, this is the feature that's causing our significant snow event for the Thursday-Friday time frame. But getting back to the temperatures, we should have warmer temperatures here and colder temperatures over here. So the jet stream will split the warmer air from the colder air. So on the surface, this is the forecasted 2-meter temperatures for 7 p.m. on Friday, the 3rd of April. And they have Grand Forks at 27 degrees and Fargo at 26 degrees, Minot 27 degrees, Winnipeg 21 degrees. And again, if we go back, that whole area is on the cold side of the jet stream. And then over to the right, Chicago's 61, Indianapolis 62. They're on the warm side. And if we go back to the jet stream flow pattern, you can see the warmth is in this area. So there's a good correlation between where we have the colder air and on the surface and the warmer air with the basically jet stream. If I take another look at it and draw it in for you, the jet stream flowing just like this. So cold air versus warm air. Okay, so those two charts were at 7 p.m. on April 3rd. This chart, we're out a little bit further in time. This one is going to be for April 6th at 7 p.m. So the jet stream flow pattern has shifted a little bit. Now we have the polar jet working through here, and we have the subtropical jet working in this area. So what I'd anticipate on the surface, we're probably going to have some colder than normal air in this vicinity. So we'll take a look at the state of Nevada. We got a ridge building, and so this should be warmer air, and it should be really nice and warm in the southern part of Texas through Louisiana. So the forecasted 2-meter temps for this exact same time frame at 7 p.m. We can see that there's quite a bit of cold air in the Nevada. There's 39 degrees, and again this is at 7 p.m. Central Daylight Time. Grand Forks, it looked like we were going to get a little bit warmer because we're into the ridge, and the jet stream did move up into southern Canada. The temperatures are 44 and 41, but they're not as warm as they could be because these computer models do take into account where we have snow on the ground. And so with Grand Forks anticipating 4 to 6 inches of snow over the next couple days, once we get to April 6th, the ground will still be white with snow. But if we back up, look over further to the east like Wisconsin, through Illinois and Indiana, where they won't have snow on the ground, and look at those temperatures. Chicago 63, Indianapolis 67. And then I also stated that it should be really nice and warm down through southern Texas to Louisiana because they're actually on the south side of the subtropical jet stream, and there we have temperatures at 80 degrees and a lot of mid-70s in that part of the country. And again, these temperatures are for 7 p.m., so a bit beyond peak heating. Okay, so the other jet stream that we need to talk about is the low-level jet stream. This one, it can occur in the winter season as well, but we're concentrating on the summer season. So we're going to take a look at the central plains of the United States during the summer, and this is a nighttime phenomenon when this low-level jet forms. It's only going to be a few hundred meters above the surface. We're probably going to look at some area between 2,500 up through about 5,000 feet above ground level. We'll take a look at the importance of the terrain in helping aid in the movement of this low-level jet. And the importance of it is that it could help create nocturnal or overnight thunderstorms. So the low-level jet, on average, somewhere between 3,000 and 5,000 feet. Wind speeds could approach 50, maybe even as high as 60 knots. And note the arrow is pointing from the Gulf of Mexico up towards the northern plains. Why it is moving in this direction, in part, is due to the Rocky Mountains being located right through here. And so that kind of forces the air to move northward in being kind of parallel to the elevation change. So why is it an overnight occurrence? Well, we will have radiational cooling on the surface, so we'll get our coldest temperatures on the surface, and then it can stay warmer above us. So we develop this radiational inversion. And this low-level jet likes to form just above that inversion. And again, it'll pick up speed as the temperature contrast increases from the surface up to a few feet above the surface. Now, how this can aid in developing thunderstorms, it's because of what's happening kind of on the leading edge of this low-level jet. Now, number one, it is transporting water vapor from the Gulf of Mexico up through the plains. It's also providing some warmer air, so warm air advection is also occurring with this low-level jet. And then on the leading edge, we have what we call speed convergence. If you have this feature moving at 50 knots and the air ahead of it's only moving at 20 knots, the squeeze play is on in between this region. Now we're fairly close to the surface of the Earth, So as the squeeze play is on, the motion of the air can't go down because we're too close to the surface, so the air will have to rise. So during the daytime, if this area was capped because of warm air aloft, we're unable to break that cap to create significant cloud development. Maybe during the overnight hours, this low-level jet would be enough to cause a lifting mechanism to break the cap, and then we could have thunderstorms form during the overnight hours. So those of us that grew up in North Dakota and or South Dakota and or Minnesota, you think about it, when do we get a majority of our thunderstorms? Florida, we talked about the sea breezes, and most of their thunderstorms formed in the middle afternoon into the early evenings with the convergence of the sea breezes. But up in North Dakota, South Dakota, Minnesota, a lot of our thunderstorms actually don't occur until after sunset. And so the development of this low-level jet during the overnight hours is responsible for some of that thunderstorm development. Okay, let's switch gears. Let's get into a little bit about the ocean currents. Won't spend a lot of time on this one, but the reason we will, because ocean currents will help move excess heat from the equator northward and a deficit of energy northward, southward. So like air movement, wind transports warm air advection and cold air advection, we will have warm and cold currents which will do the same thing. So wind drags the surface water. Ocean currents are slower due to friction with deeper water. Currents will flow in a circular whirls called gyres. Flow is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Okay, what atmospheric pressure systems would be associated with the movement of the currents? In other words, which flowed clockwise in the northern hemisphere, the high or the low pressure system? Well, it's the high pressure systems. And in the southern hemisphere, high pressure systems rotate counterclockwise. We'll investigate. So here are the major currents of the world. What's located out here? The Pacific High. What was located over here? The Bermuda High. Both turning in a clockwise fashion. Blue, cold currents. Red, warm currents. The three main currents that affect the United States. Off of California, it is simply called the California current. Warmer waters in the Caribbean into the Gulf of Mexico and the Caribbean, that water will rotate up and turn out to the northeast. Water from the Gulf of Mexico will squeeze through Florida and Cuba and take off and go in that direction. So that's a warm current. That's called the Gulf Stream current. And the last one up here, the Labrador current, that'll be the colder waters sneaking in to the New England states. So there's a key cutoff kind of right here around Cape Hatteras, North Carolina. So this water is fairly cold and this water is nice and warm. Now know where the Gulf Stream current goes. Through the North Atlantic, and then it takes off well into the northern latitudes. Okay, now I want to point out something. Grand Forks, I'll get us in the ballpark here. We're located about here. Okay, Grand Forks. And if we come straight across, so I'm going to be on the same latitude best I can. See where London's located? London is further north in latitude than Grand Forks, North Dakota. How many days do these people experience temperatures below zero? And the correct answer is never. Norway, Sweden, are they as cold as us? Nope. Wow, they're a lot further north. but they get the modifying effects of the warmer waters as the air moves in this direction because of the Gulf Stream current making it that far north. So again, water can have a modifying effect on local climates. So the ocean circulation patterns will transport a significant amount of heat energy poleward and equatorward. So about 40% of the work will be done by the ocean currents, 40% will be done by the wind, and the other 20% is done through the latent heat processes that we talked about in chapter number 2. So the ocean currents will affect local climates, and they can contain boundaries as well. So this is an infrared. The red shows the warmer waters of the Gulf. You can see how it's moving. And this pinkish color in blue, these are the colder waters, and they're sneaking in this direction. So there's Cape Cod, there's Long Island, there's Cape Hatteras, and so that's kind of where the split-off point is. So if you don't want warmer waters and the nice beaches, I guess that's why we like to vacation in this area versus vacationing in this area. Now obviously we vacation up there, but don't expect the sea surface temperatures to be all that warm from Long Island up through Cape Cod, Massachusetts. Now if we go to the other side, to the California coastline, we did take a look earlier and we saw that when we talked about advection fog, that the temperatures were relatively cold on the surface of the water right next to the coastline of, let's say San Francisco up through Mendocino. So what's going on is the California current is rotating in this direction, and the mass movement of the water, even though the current's moving like this, the mass movement of the water is going to be from near the shore to offshore. With that occurrence going on, the colder water must come up from below to replace the water that is moving off in this direction. So that upward motion is what we're going to call upwelling. So you can see it here with these blue arrows. We'll pull that colder water from down below and pull it up as the warmer water gets pulled out to the west. So again, the name of that is called upwelling. So and that accounts for the extremely cold water right off of San Francisco Bay up through Cape Mendocino. And so being the warmer waters out here, and we have westerly winds on the surface, that warmer moist air interacts with the colder temperatures, then you get your fog, and then the fog can move inland a little bit, and you get a lot of advection fog along the Pacific coastline. So substantial amounts of heat are transferred from the ocean to the atmosphere in the winter. This provides energy for atmospheric winds. Thus, changes in ocean surface temperatures affect global weather. This is fairly new science. This is what we call the teleconnections. So how these sea surface temperatures are changing in various parts of the world, we're starting to figure out how it affects pressure patterns and how those changing pressure patterns can affect long-range outlooks for forecasting. So we're going to pick on just one of these teleconnections, El Nino versus La Nina. So they're named after the warming in the ocean temperature off of South America occurring at the end of the year, now known to refer to large-scale warming of the eastern Pacific. So El Nino, the water is getting warmer than normal, but it's hard to predict when that will occur because it could be 2 or it could be 7 years apart. But we do understand now that it does affect large-scale weather patterns. So in the normal year, high pressure would be over the eastern Pacific. We'd have our trade winds that we talked about in the 3-cell model. The warm surface water would be to the west, and then we'd also note a difference in sea level as well. So this kind of ties it all together. This is normal. if the sea surface temperatures were where they're supposed to be, we'd actually have a thermal high pressure system situated right off of South America. So let's get our bearings here. This is Central America. Panama Canal would be located in this vicinity. And so we got Peru and Ecuador lined up over in this area, and we're kind of watching the equator, that area. So the colder water, that would cause cooler temperatures above the sea surface. Diverging air, sinking air, there's your thermal high pressure system. The northeast trade winds, southeast trade winds, again this is the equator. And then over in Indonesia we'd have converging air due to a thermal low pressure system and rising air. So you'd expect an area of precipitation occurring over in the eastern side. This is normal. So what happens when these waters off of South America and along the equator get to be warmer than they should be? Well, they're going to lower pressure over the eastern Pacific, weaken and maybe in reverse the trade winds. Warmer water from the west carried eastward in a thing that we call a Kelvin wave. So this is El Nino. The big thing to note is a reversal of the pressure systems. When it was normal, we had high pressure over here. Now we have low pressure, and the high pressure is over here, because this water is now warmer compared to the water over here. So in the warmer waters, we'll generate a thermal low, converging upward, precipitation. Air has to go from the high to the low, so look what happened to the trade winds. They actually could reverse in direction in that situation. So if these pressure patterns are reversing, then you can have a chain reaction, and that can cause pressure patterns to change elsewhere around the world. So we call this ENSO. Pressure pattern reverses after a year or so. Seesaw pressure changes is called the Southern Oscillation. You combine that with the surface water warming that we called El Nino, plus Southern Oscillation, that's where the ENSO comes from. Now, if we had abnormally cooling, we would call this La Nina. So I'll show you what kind of weather can we expect with these two scenarios. Now, the first one up, El Nino. Again, get your bearings. Good old Grand Forks. We're located right in this vicinity. And when the waters off of South America are normal than they should be, El Nino, look what happens. The subtropical jet stream is the red one, and the polar jet stream is the purple one. Where's the cold air versus the warm air associated with the axes of these jet streams? Cold air on this side, warmer air on this side. So you can see Grand Forks vicinity, we're in a warmer than normal situation. That is El Nino. Now if we go to La Nina, now we have the subtropical jet stream and the polar jet stream. So to me it looks like the Pacific high is stronger than it should be during the winter season because it's pushed a little bit further north. And so that's going to drive the polar jet stream up through Alaska into the Northwest Territories, grab onto some cold air, and then pull that cold air into the Grand Forks vicinity. So when we have this pattern, La Nina, Grand Forks' winters typically are going to be colder than they should be. Now the southern states, they will be warmer because of the displacement of the subtropical jet, but they're also going to be on the drier side. Now it doesn't occur always, but we're getting a little bit better handle on it the more years of data that we collect. So I just want to show you some stats to see how this is panning out just for the Grand Forks area. Here we have green color along the equator. Those temperatures are below normal, and so this is what we're going to call La Nina. So this is a moderate La Nina event for the winter of 2010-11, a while ago, a decade ago. So what I did is I found some stats, and I took a look at November through March. This is average temperatures for those months, and here's what happened. 1 month, November, was just 1 degree above normal, but December, January, February, March were all below normal. So if we did the total of those 5 months, Grand Forks had an average temperature that was 3.3 degrees below average. Okay, what did we say about La Nina? Grand Forks would experience temperatures below average. And so it worked on that particular season. This one's neutral. So we don't have either. We don't have La Nina. We don't have El Nino. Everything's kind of around 0, so it's fairly neutral. So this is a non-predictor. It's very difficult to tell the general public what kind of winter we were going to have in 2013 and 14. Well, what actually happened? It was cold. Every single month we had below normal temperatures, with December being 11.6 degrees below normal. So overall, the whole winter, and realistically winter is only December through February, but I took the months on either side of that as well. But in those 5-month period, 7.6 degrees below average. Pretty tough winter for us in the Northern Plains. So this is what we'd like to see. We want to see these waters to be above normal. In this case, we had temperatures 2.5 up through about 4 degrees Celsius above normal. So this was a moderate El Nino event in 2015-2016 winter. So this should dictate above normal temperatures for the winter up here in good old Grand Forks area. How did we do? One of the warmest winters we've experienced in the past couple decades. Every single month was above normal, with March being almost 11 degrees above normal. So 8.1 degrees above normal overall. Very impressive. And this was 2018-19, weak El Nino, so that would be a predictor for being above normal temperatures. The National Weather Service outlook for the 3 months of winter did have us above normal temperatures, and we were above normal in December, but the other months it didn't work out. February, very cold, 6.2 below average. So again, it wasn't a strong indicator. It was fairly on the weak side, and so in this case it didn't work out so well. Why? Well, by the time we got to January of 2019, the latter part of winter, it dissipated. We went back to neutral. And so the weak El Nino that was setting up in the fall fell apart before we actually got into the brunt of winter. Now this past winter, we're in the neutral phase. We switched satellite imagery here, but you can see the oranges and the blues are all kind of sitting right around 0. And so this was fairly neutral. And later on, when we got into the November time frame, it was still fairly neutral. And so the Weather Service kind of went that way too. They kind of put us in the, for both precip and for temperatures, they gave us an equal chance of being above or below. And I just did some stats for you. And this is what occurred this past winter, including the March that just concluded. We were below normal 4 of the 5 months, but overall only about 0.9 degrees below average. Precipitation, as you know, when you were here, we had pretty good precipitation in December into January, and then we got dry and we went below normal, and so even the precipitation turned out to be fairly normal for the year. So again, just a little bit on how we use these teleconnections to try to give a winter outlook for different parts of the world. So that is chapter number 10. So we did it in 2 videos. Those are the key terms. Make sure that you take a look on the Easy LMS site. You'll notice that there is a quiz scheduled for chapter number 9, but I do not have a quiz scheduled for chapter number 10. I'm just going to tie chapter number 10 right into test number 3. So also take a look at the date and time that test number 3 will be occurring in the middle part of April. I think it's all going to occur before April 9th. I want to get these tests completed before the last date to drop, which is April 9th, in case some of you are kind of on the bubble and need to make a quick decision. Okay, so I'll hold off on working on chapter 11 until we complete the test for chapters 8, 9, and 10. Okay, stay safe out there, stay healthy. Bye-bye.